This Calc 2 lecture is on polar coordinates. You should have done a lot of this work in pre-calc, I hope, and therefore this should just be mostly a review. All right, you are used to Cartesian. I don't like that color. So you are used to Cartesian coordinates. X, Y. Today we're talking about polar coordinates. So some point, we'll call it P, in a polar coordinate system has coordinates that look like this for the ordered pairs, r theta. When you are plotting points on a polar system, the pole is a point and it corresponds to the origin. And again, we just call it the pole. You're used to X and Y axes. Well, we have a polar axis, but it's only a ray, it's not a line. And it is drawn from the pole, and it corresponds with the positive x-axis. If you have a polar coordinate, r theta, and r is a positive, that means that it's the distance from the pole, r is. Theta is always an angle that's formed by the polar axis, so the positive x-axis, and another ray that goes from the pole through the point. So if here's my point P, and here are it's in coordinates r comma theta. R is this distance, and theta is this angle measured from the polar axis to the ray that contains the point. The initial side of the angle is on the polar axis, and the terminal side of my angle goes through the point. We call r comma theta the polar coordinates, just like we call x, y the Cartesian coordinates. So if we have some point P and its polar coordinates are 2 comma pi over 4. I'll give you a hint. I always draw out my angle first. Then I count out r. So in other words, I will start with the initial side of my angle on the polar axis. I rotate pi over 4 degrees, pi over 4 radians, which is 45 degrees. On this ray, I count out a distance of 2. Now, polar coordinates are not plotted on rectangular coordinate systems. They're plotted on a grid that has concentric circles, and every concentric circle has the pole as its center. And again, as I mentioned, it's easiest for most students to draw the terminal side of the angle and then count out the number of degrees. So here I have what is shown to you as a grid of circles. Here is my pole, the same angle that I plotted before. Here's the angle measure the angle that has its initial side at the pole, and each one of, these darker spokes here, you see those? Those are each 30 degrees on this particular graph. So if I want to plot a 45-degree angle, that's going to be right here. So the terminal side of my axis of my angle would be right here. I'm counting off 2 concentric circles. So here's the first concentric circle. Here is the second concentric circle. So here is my point P. Just drawing those red circles so you can see them a little bit better. So that point would have the coordinates 2, pi over 4. So let's actually graph. These concentric circles that you see on the graph below are very, very lightly shaded, and there are no angle measures sketched in for you like spokes on a wheel. So let's first plot the the polar coordinates for 3, 7 pi over 6. Because this is a 6 in the denominator, I know that this is a 30-degree reference angle. Because the number in the numerator is 1 larger than the denominator, I know that this angle is in quadrant 3. So I need a 30-degree reference angle drawn in quadrant 3. So this angle right here would be 7 pi over 6. I need to count out 1, 2, 3 places. So here is the point whose coordinates would be 3, 7 pi over 6. All right, let's graph the other angle. Let's graph 2, negative pi over 4. You know that if you are graphing an angle who's got a radian measure that's negative, that you are rotating clockwise as opposed to counterclockwise. Because that's a 4, you know your reference angle is a 45-degree reference angle. So I am rotating clockwise, so in this direction, and I am drawing a 45-degree angle. So this angle right here would be negative pi over 4. And then I need to plot 2 concentric circles. So here is my point. This point has the coordinates 2, negative pi over 4. So at this point, you should feel comfortable plotting points whose R value is positive. So what happens if R is a negative number? It's less than 0. The point's going to then be on a ray that is not on the terminal side of the angle. It's in the opposite direction of the terminal side of the angle. You still want to plot your angle measure first. Then you're going to mark off your R units as if the angle measure was going in the opposite direction. And one of the things that helps me graph polar coordinates when R is negative is to think about walking backwards from the pole instead of forward on the terminal side of the angle. So let's go back a couple pages and let's graph our point, which is negative 2, pi over 3. So I know that this is a 60-degree reference angle because that's a 3. So that means that my angle measure, all right, there's the terminal side, the initial side. Here would be the terminal side of my angle. I am starting here at the pole. And instead of counting out 1, 2 concentric circles, I need to go in the opposite direction. So I need to go in this direction, counting out 1, 2 concentric circles. So the point whose coordinates are -2, pi over 3 would be located right here. Rectangular coordinates, like 5, -1, can only be expressed in one way. I can't write that as -7 over 3 and say that's the same location, because it's not. Rectangular coordinates can only be expressed one way. However, polar coordinates can be written multiple ways. So let's go back to our polar grid. And keeping your notes open to the bottom of page 2, let's graph these points. 2, pi over 6, 2, 13 pi over 6, 2, -11 pi over 6, -2, 7 pi over 6. So the first one that I'm going to graph is this one, 2, pi over 6. All right, here's the initial side of my angle. 30 degrees would be right here. Here's the terminal side of my angle, counting out 1, 2. So this point right here has the coordinates 2, pi over 6. All right, now let's graph 2, 13 pi over 6. Are you comfortable that 13 pi over 6 is more than one rotation? So in other words, I would be rotating 12 pi over 6, 13 pi over 6, and that point right there has the coordinates 2, 13 pi over 6. Now let's graph 2, -11 pi over 6. -11 pi over 6 means I am not rotating counterclockwise. I'm rotating clockwise. So from my initial side of my angle, I am rotating 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And I am counting out 2 concentric circles. So the point 2, -11 pi over 6 is also at that same location. Finally, let's graph -2, 7 pi over 6. All right, 7 pi over 6. So I am rotating pi over 6, 7 pi over 6. But I am not walking from the pole in this direction. That's not the way I'm going. I need to go in this direction, 2 concentric circles. So there's my point. So the point -2, 7 pi over 6 is also in the same location. We have 2 more tasks in this section. We need to take polar and rectangular coordinates and go from one to the other, and then vice versa. So that will be my first task, to convert from polar coordinates to rectangular coordinates. So right here, I'm going from r, theta. That's what I'm going to be given, an r and a theta, and I have to change that to an x and a y. I like to draw a triangle in the quadrant where the polar coordinates would be plotted, and then use the idea of my special right triangles, 30, 60, 90, and 45, 45, 90, because I know those relationships. If you choose not to do that, that's fine. You can use these two ideas from trig, that x is equal to r cosine theta and y is equal to r sine theta. So I will do each of these problems both ways. So let's start here. Here is my r comma theta. So if I make a quick sketch of this, this tells me that the initial side of my angle is here, the terminal side of my angle is here. It's a 30-degree angle. Because this is positive, I need to go out 6 units. So here's my point. So if I drop down a perpendicular, I know that this is 6 and that this is 30 degrees. And I know that the side opposite the 30-degree angle is half of the hypotenuse. And I know that the side opposite the 60-degree angle is the side opposite the 30-degree angle times the square root of 3. So let's look at my coordinates for x's and y's. Here's my x value right here, 3 square roots of 3. Here's my y value right here, 3. Let's do this again using the idea of cosine theta equals x over r, so therefore x is equal to r cosine theta. So if x is equal to r cosine theta, then x would be equal to 6 times the cosine of pi over 6. So x would be equal to 6 times the cosine of 30 degrees. The cosine of 30 degrees is the same as the sine of 60, square root of 3 over 2. So x is 3 square roots of 3. Y would be equal to r sine theta. So y would be equal to 6 times the sine of, I'm just going to write the 30 degrees there. So y would be equal to 6 times a half, or y would be equal to 3. So again, you can see my coordinate down here at the bottom lower left of the screen. X is 3 square roots of 3, y is 3. All right, let's do the problem over here on the left. Excuse me, the right. So I'm going to graph my polar coordinates. Theta is negative pi over 4. So here's the initial side of my angle. Negative pi over 4 would be right here. But because this is a negative, I need to go in this direction. So going out 4 units would put my point right there. So I'm going to drop a perpendicular. I know that this was a 45-degree angle, so this is also a 45-degree angle. I know that this was 4 units long. I'm not writing it as a negative 4, I'm writing it as a positive 4 because it's a distance. So in a 45, 45, 90 triangle, both of the legs are the same. It'll be 4 divided by the square root of 2. So 4 square roots of 4 divided by the square root of 2. So I'm going to rationalize my denominator because I can tell I'm going to be able to simplify. So my sides are 2 square roots of 2. Both sides. Now, again, this is r comma theta. So xy would be equal to, all right, here's my x. Negative 2 square roots of 2, positive 2 square roots of 2. If you would like to do this with r cosine theta and r sine theta, you will get the same values. So now let's go the other way. Let's go from rectangular to polar coordinates. To go from rectangular to polar, I still draw a triangle, but I draw my triangle based on the point given in my rectangular coordinates. And then I use my relationships for my special right triangles. However, you are also welcome to use these two trig relationships that you know. So let's do the first one. I'll do it for you both ways, and then we can do the second problem. 2 comma negative 2. Okay, there's my point right there. So from the pole, yeah, all right, let's see. I'm going to make a perpendicular here, maybe. There we go. So I know that this distance right here is 2 and this distance right here is 2. So if this is a 90-degree angle and the legs are the same length, I know it's an isosceles triangle and that this has to be a 45-degree angle. I know the relationship between 45, 45, 90-degree triangles is, let's erase these for a second, is 1, 1, square root of 2. So I just need to take this leg and multiply it by the square root of 2, and that will be my hypotenuse of my triangle, which will be my distance. In other words, my r. So these are the xy coordinates, the polar coordinates. Let's do my angle first. I'm going to rotate in clockwise direction, so this would be a negative pi over 4. My r value was 2 square roots of 2. Now, there's other ways that you could have done this. Please understand that you could have said that your angle measure was 7 pi over 4, but r is still 2 square roots of 2. But this is probably the answer that I would have chosen. Now, let's use my trig relationships instead of my right triangles to help me do my problem this time. R squared is equal to x squared plus y squared. So, r squared is equal to 2 squared plus negative 2 squared. So 4 plus 4, or r squared, is 8. So r is equal to the square root of 8, or 2 square roots of 2. Tangent of theta is equal to y over x. So the tangent of theta is equal to negative 2 over 2, or the tangent of theta is equal to 1. So arctangent of negative 1 is equal to theta. So theta is equal to negative 45, or negative pi over 4. Your calculator will not give you that answer there of 7 pi over 4. Again, I just prefer my triangles, but it's completely up to you as to what you use. So let's look at my second point and find those polar coordinates. So I am plotting here negative 1 square root of 3. So that's about right there. Negative 1, negative rad 3. So there's my angle measure. This side is 1. This side is the square root of 3. Drop my perpendicular right here. My angle measure here let's see if I can draw it right here. Come on, there we go. That reference angle I can tell with the 1 and the rad 3 that using the Pythagorean theorem, my hypotenuse will be a 2. 1 squared plus square root of 3 squared. I don't even want to call it R. Let's just call it C for hypotenuse, what you guys are used to. So 4 equals C squared, so C is equal to 2. All right, theta reference there. Since I am across from the rad 3, I know that that is a 60-degree reference angle, so there's going to be 3 in the denominator. I know that since I am in quadrant 1, 2, 3, that this is going to be a 4 pi over 3. The numerator will be 1 larger than the denominator. So I know that this 30-degree reference angle in quadrant 3 would be 4 pi over 3. And R was 2. So again, I prefer using method 1. You may use what you would like. Doesn't matter to me. Our last job is to change a equation that's either given to us with polar coordinates or rectangular coordinates to the other form. So when we are going from a polar equation to a rectangular equation, again, equations here, not coordinates, we have some trig that will help us. X is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared. Now, when you are going from polar to rectangular, you've got 2 techniques. You can use this, or you can use this. Those are the only 2 things you are allowed to do that's going to get you anywhere, changing from a polar equation to a rectangular equation. You're going to pick one of those 2, and then you are going to look for these relationships. So let's try squaring both sides. Let's see what happens. We get r squared is equal to 4 cosine theta squared would give us 16 cosine squared theta. Well, this is helpful because I know that, but this does not look anything like either of these 2. It's got a square in it. So that did not work. So this time, instead of squaring both sides, let's try to multiply both sides by r. So I would have r times r equals 4 times r times cosine theta. So I would have r squared equals 4r cosine theta. Well, this is helpful because I see it right here. And look, this I see right here. So I am going to substitute in place of r squared, x squared plus y squared, and in place of r cosine theta, I get to put an x. Now you should recognize that equation. You should be saying to yourself, oh, an x squared plus a y squared, both positive, this thing has to be some kind of a circle. So let's put this in a form where I can tell something about my circle. I am going to move my 4x to the left side of my equation. And I am going to complete the square on my x's. Half of 4 is 2. 2 squared is 4. So I am going to add 4 to both sides of my equation. I'm going to factor this trinomial because it's a perfect square trinomial. And I recognize this circle for exactly what it is. It is a circle whose radius is equal to 2 and whose center is 2, 0. All right, let's do another one. Bottom left-hand side of the page, we have that r is equal to 2. Well, let's try squaring both sides again. So that would give me r squared equals 2 squared, or r squared is equal to 4. Well, we know what r squared is equal to. It's equal to x squared plus y squared. And I recognize this. This is a circle whose radius is equal to 2 and whose center is at the origin. Our last task is to go backwards from a rectangular equation to a polar equation. And you just need to manipulate your equation around enough so that you can get these relationships. Now remember, this is a rectangular equation. That's why you see the x and the y. We want a polar equation, so our answer needs to have r's and thetas in it. All right, let's look at our equation here. 2x squared plus 2y squared equals 3. I see an x squared and a y squared, which tells me I want to aim for this, but it's not quite in the right form. However, if I factor the 2 out, I can write x squared plus y squared equals 3 halves. And since x squared plus y squared is equal to r squared, that means my polar equation would be plus or minus square root of 3 halves. You don't need to worry about rationalizing the denominator. All right, let's do the last one and finish up this lecture. I think this is the hardest problem we're going to do all day. We have x equals 4. Oh, x is just r cosine theta is equal to 4. You're finished. That is your polar equation. So, practice your homework, see what you need help with, and let me know. This ends the section 11.3 Polar Coordinates lecture.